A standard push-up is a highly complex, closed kinetic chain compound movement. Executing it properly requires the entire skeletal structure to stabilize under intense load. The primary controller of the torso's descent is the pectoralis major. This muscle utilizes both the clavicular head, near the collarbone, and the sternal head, spanning the mid-chest, to manage the downward force. As the upward press begins, the anterior deltoids handle adduction, actively driving the arms inward toward the center of the chest. Midway through the upward phase, the triceps brachii take over the primary mechanical load to force the elbows into full extension. This pressing motion is the concentric phase. The muscle fibers actively shorten to lift the anatomical load against gravity. The descent is the eccentric phase. Here, the fibers undergo controlled lengthening, creating the microscopic muscle tears responsible for delayed onset muscle soreness. The push-up applies a systemic structural load to the body. It demands simultaneous, multi-joint coordination rather than isolated chest activation. Supporting the prime movers requires a rigid kinetic chain. The rectus abdominis and transversus abdominis act as anterior anchors, locking the pelvis in place to prevent the midsection from collapsing toward the floor. On the posterior side, the erector spinae and deep multifidus muscles engage to keep the torso completely erect. Together, these muscles establish spinal neutrality. This anatomical alignment is the mechanical prerequisite for generating and transferring force safely. Throughout the entire repetition, these core groups remain in a state of constant isometric contraction. If that isometric tension fails, the hips sag, breaking spinal neutrality and improperly loading the lumbar vertebrae. The core musculature functions as the essential structural bridge, ensuring force transfers safely between the upper and lower extremities. Altering the ground surface beneath the hands immediately shifts how the central nervous system distributes the athlete's neuromuscular load. Clinicians measure this engagement using maximum voluntary isometric contraction, or MVIC. Performing a push-up on a stable floor yields maximum prime mover activation because the central nervous system does not have to throttle force output to maintain balance. Introducing suspension training variables, specifically single anchor systems utilizing unstable pulleys, forces the body to solve for gravity and lateral motion simultaneously. This chart visualizes clinical data by Calatayud and colleagues. It shows pectoralis major and anterior deltoid activation drops sharply under suspended pulley conditions. Conversely, triceps and upper trapezius activation spikes significantly to counter instability. The extreme outlier in this data is the rectus abdominis, which registers an activation rate exceeding 60% MVIC on the pulley system. Lateral instability reprioritizes the muscular roles required across the kinetic chain. Instead of acting purely as elbow extensors, the triceps are forced to work continuously as lateral joint stabilizers. The latissimus dorsi heavily engages to lock the shoulder joint in place and resist the swinging pendulum effect of the stress. To maintain mechanical equilibrium around the highly vulnerable lumbar spine, the abdominal muscles must drastically overcompensate. Dual anchor parallel band systems offer a moderate middle ground, inducing less extreme MVIC spikes than pulleys while still challenging the stabilizers. Highly resistance-trained individuals possess efficient motor unit recruitment, meaning they might not experience these same extreme MVIC spikes as novices. Pulley suspension systems also increase activation in the rectus femoris and lumbar erector spinae. Researchers note that without sufficient abdominal engagement, this increased tension on the pelvis can result in an exaggerated lumbar arch. Introducing environmental instability shifts a significant portion of the mechanical load toward the systemic stabilizers, making the core's role in the movement as demanding as the chest press itself. Adjusting the angle of the pressing vector creates an entirely different neuromuscular response, particularly in the decline push-up. Elevating the feet shifts the torso tilt downward, causing the arms to press upward and slightly forward relative to the chest. This geometric overlay demonstrates how the line of force during a decline push-up aligns directly with the orientation of the clavicular head fibers in the upper chest. This specific mechanical alignment increases the neuromuscular activation of the clavicular head while reducing the dominance of the sternal head. By altering the pressing vector, practitioners can selectively dictate which anatomical muscle head assumes the primary mechanical load. Beyond localized muscle mechanics, this massive level of muscular recruitment generates a systemic metabolic cost across the entire human body. A 2014 clinical study by Vizina and colleagues at Arizona State University evaluated the true energy expenditure required to execute resistance training. The researchers utilized metabolic equivalents, or METs, as the clinical baseline to measure oxygen and energy consumption. This graph compares two models of energy measurement. The lower line represents the traditional method, which tracks oxygen consumption during the actual activity. The higher curve represents the non-traditional calculation, or NEC, which calculates the average oxygen consumption recorded during the recovery period. Under the NEC calculation, standard push-ups generate an energy expenditure of 6.9 METs. This specific MET value formally categorizes the push-up as a vigorous intensity exercise, requiring an energy output on par with heavy cardiovascular training. The micro-damage sustained by the muscle fibers during the eccentric phase creates an oxygen debt. The body must spend additional calories to repair this tissue long after the set is finished. The metabolic demand of a push-up outlasts its mechanical action, establishing the exercise as a powerful driver of systemic energy expenditure. A persistent misconception is that utilizing the push-up will target and burn localized belly fat or adipose tissue around the chest. High localized muscle activation in the pectoralis or the rectus abdominis does not metabolize the adjacent adipose tissue. The physiological mechanism of fat burning, known as lipolysis, operates systemically, not locally. The high metabolic cost of the exercise triggers the release of hormones and enzymes that break down stored fat from anywhere in the body to meet the energy demand. This diagram shows stored triglycerides as they break down into free fatty acids and release into the bloodstream. Once in the global circulatory system, these free fatty acids are transported back to the working muscles to be oxidized for fuel. While push-ups drive a powerful systemic caloric deficit, the location of that lipid oxidation is genetically predetermined. The fat is burned independently of the specific muscles doing the work.